Hi guys, welcome back to Aisha.Academy, and in today's video we're going through modelling with exponentials and logarithms. So I released a video on exponential and logarithms, but this is with modelling them on a graph now, more in detail. So my question to you is, does E have to be used in exponential growth or decay? The answer is no, but using it does make your life easier. So I'm going to give an example of this. So for instance, if a question says write a quarter to the power of x in the form e to the power of minus kx and work out the value of k, the first thing we're literally going to do is make the quarter to the power of x equal to e to the power of negative kx. And now that we've done that, what we're next going to do is we're going to rearrange the quarter to the power of x as 4 to the power of minus 1, because a quarter can be written as 4 to the power of minus 1, and then still have the brackets to the power of x, and then you've still got that equal to the e to the power of minus kx. And the next thing we're going to do is that the 4 to the power of minus 1x, we're going to change that to 4 to the power of minus x, because multiply the two powers, and then that's still equal to our e to the power of negative kx. So now, where it's going to change is we're going to add ln to both sides, so natural log to both sides. And that's going to change it to ln 4 to the power of minus x is equal to ln e to the power of minus kx. Now, the ln 4 to the power of minus x is going to change to minus x ln 4. Remember, watch the video on laws and logs to refresh your memory of why that's the case. And then the ln e to the power of minus kx will change to minus kx ln e. The x's on both sides are going to cancel out. And also ln e is equal to 1, so that's going to cancel out as well, leaving us with ln 4 is equal to k. So k is equal to 1.39 if you put that into your calculator. And that's to 3 significant figures. So if a question now said, following on to that, state whether the quarter to the power of x would represent exponential growth or decay, looking at the scenario, because the power to the e is a negative power, right, it's going to be a negative exponential. And so remember, negative exponentials are exponential decay. So when it comes to exponential modelling now, this is basically shown on a graph, aka is it going to be shown as exponential growth or exponential decay, which I mentioned briefly in the other exponential and logs video. So exponential growth can be used for population growths, it can be used for compound interest, and whereas exponential decays is usually used for things like radioactive decay of like particles, depreciation of like land, or like, well, land doesn't usually depreciate, but cars do, or like drug metabolism in the body. So here we have an example question. It's given us this formula and it wants us to write down the value of A. It says that the scientists released 24 rare birds in the newly constructed nature reserve. So 24 would be equal to B, and then that's that T is equal to 0. So then substitute those values in, and that would leave you with A is equal to 4. And then it now says how many birds will be in the reserve after 24 years. Sorry, after 2 years. So then we need to substitute 2 as T. And by doing that, you'd be left with this value, 53.4129, which would round up to 53 birds. And then it says how many years will it take for the bird's value to double after their release. So if it's in terms of doubling, then B would be equal to 48, because 48 is double of 24. So then you would substitute that 48 for B, into the formula. So then 2 would be equal to e to the power of 0.4t. You would then want to add ln to both sides. So there would be ln2 is equal to ln e to the power of 0.4t. ln2 would be equal to 0.4t. ln e would cancel out. So you'd be left with that. Do ln2 divided by 0.4 in your calculator and you'd be left with 1.73 years to 3 significant figures. Okay, so we've talked about exponential modelling, but log graphs can also be used for exponential modelling as well. So this is because log graphs are straight line graphs, so sometimes they're easier to interpret compared to the curvature graphs that exponential graphs give. So this would be like an example of your e graph. So like y is equal to e to the power of, I don't know, 0.1x. But if we were to change this into a log graph, this would actually become a straight line graph. And for that specific equation, it would be ln y is equal to 0.1x plus ln 3. So how is this? Because if we have 3e 0.1x, and we add ln to both sides of the equal sign, this would leave us with ln y is equal to ln 3e to the power of 0.1x. Remember, if you're multiplying two things with logarithms, the same thing as adding them. And then the ln e to the power of 0.1x, that power would come to the front. Ln e is going to cancel out, leaving us with ln y is equal to 0.1x plus ln 3. And one thing I want you to notice is that this is in the form of y is equal to mx plus c. And so because it's in that format, that's our format for a straight line equation. And that's why it's a straight line for log graphs. So when it comes to, for instance, exponential growth, this is usually where you have a positive power. So for instance, y is equal to ab kx to the power of kx. Exponential to decay, it would be a negative power. So y is equal to ab to the power of minus kx. And this value of b, bear in mind, in exponential growth and decay, is got to be a constant greater than 0. So there's 3 scenarios of converting exponentials into logs you need to be aware of. The first type is that if you have y is equal to a, b the constant, so a times b the constant to the power of kx, add log b to the both sides because b is the base, right? So that's going to be log by is equal to log b ab to the power of kx. Again, multiplying logs, same as adding them together. Look at the video of laws of logs to refresh your memory on this that I posted 2 weeks ago. So that will be changed into log ba plus log b to the power of kx. Remember, powers with log laws end up moving in front of the log, so it's going to change into log by is equal to log ba plus kx log bb. The log bb is going to end up cancelling out, it's the same as 1. So then, therefore, that's going to leave you with log by is equal to kx plus log ba. And still notice that y is equal to mx plus c format with this answer. So the second type of scenario is more to do with if you're given in a formula where rather than be a constant, your constant is e. So remember, when we're dealing with e's, rather than using log, we use natural log, ln. So substituting the ln, leaving you with ln y is equal to ln a plus ln e to the power of kx. Again, moving the power down, ln e is going to cancel out, leaving us with the final answer of ln y is equal to kx plus ln a. And then the last scenario is more to do with x being our base. So not e, not another constant, but the actual x. So when x is your base, you're not going to write the actual base next to the log. You don't. Because if you do that, you're going to end up cancelling out x from the final answer, which we don't want to do that with our straight line equation. So this is going to leave us with log y is equal to log a plus log x to the power of b. Power is going to move down, and then this is how we would leave it. Okay, this is the difference. So I'm going to give you an example question now. So given that y is equal to ae to the power of kt, and that ln y is equal to 4.5t plus ln 7. It wants us to work out the values of a and k. So we know that k is always the m, the gradient, so k is going to be equal to 4.5, and then a is the y-intercept, so which is equal to 7. And that's it. Okay, so now I'm going to give an example question. So here it's given us a table of values, and it wants us to basically plot the values onto the graph. Literally, all you're going to do is like just your basic knowledge of literally plotting the x and the y values onto the graph. Your y values, remember, is the ln n, not the n, and then the x with the t. And then now it's given us 2 points. So it says using the 2 points, it wants us to find the equation for the line of best fit. Okay, so the first thing we're going to do is work out the gradient, which is your general knowledge of your change in y by your change in x. So that's going to be the 7.37 take away the 4.61 over 4 minus 0. Putting that into your calculator should leave you with an answer of 0.69. Now that we've worked out m, we need to work out the LNC. So working out our LNC, we can simply substitute when t is equal to 0. LNC is equal to lnn, so at that point, which was 4.61, so then substitute that in, and that would be your final answer. So using the table of values for that. And then working out a and k, k is equal to m as mentioned before, so k is equal to 0.69 in that equation, and a is equal to c. So remember, it's equal to the c, not the whole LNC, so a is equal to 100, and that's very important to note. Okay, so I hope that was useful, guys. If I was going too quickly, or you want me to slow down, or you have any further questions, please answer in the comments. Thanks for watching, and stay tuned for more content. Please share, comment, like, and subscribe.